Good morning. We want to look at applications. Compiler is an application. So we'll look at that and show how there's very, very little that we need to do to build compilers. The compiler takes source code and produces applications. So our source code is a text file of some kind. Could be hundreds or thousands of text files, but it simply, to the compiler, just looks like one big text file and creates the binary or an emulation acceptable data structures to run and produce applications. Everything we have is an application. Everything that runs on a computer is an application, from the bootstrap to the operating system to all the services. Everything is just simply an application. And so all of our work from software development is through our compilers. So we want to take a look at that and then how that applies to all of our other applications. So we look at what a compiler does. First thing it does, it takes that source code and needs to break it up into all the individual words and syntax that a particular language understands. So in general, it will break it up into an ID. So if we have a word or a variable name, we'll call that an ID. And if we have a quoted string, we'll look at that, and whether true or false, we'll declare that as a Boolean. We might have a date formatter or math operators and so on and so on. So it takes tokens, so it takes our source file. Let's say our source file is alert hello world. Well, our tokenizer, or parser, determines that the first word is alert, and we'll tag that as an ID. Next, it finds an open paren and says, oh, that's a group, beginning of a group. And then it finds a string, which is hello world. And next it finds a closed group, a closed paren. And finally, end of statement, which is a semicolon. So all of our languages, all of our computer languages determine some sort of syntax that it wants to determine what to perform. In this case, it says, oh, I want to show hello world on the screen, or whatever it wants to do. So in our case, this is our first simple program. Next, it takes those tokens one by one and sends them to a statement analyzer. And a statement analyzer says, oh, I have different statements that I'm looking for. So I could have an expression, designate E as an expression, or it could be an assignment, A equals 1, which is a simple assignment, or a for statement, or a while, or a switch, or an if, or any of the other SQL, or whatever statement we want to look at. So all of our scripts, source codes, we have hundreds of thousands of scripts, and they all do the same thing, which is to tokenize it and then determine what actions to perform. So in our case, we determine that S is a statement, and it could just be E. So it could be an E expression, or an expression could be an ID. In our case, it would be an ID as alert, open paren, E as in a string of hello world, and then a closed paren and a semicolon. And so that satisfies the E, and then that E gets reduced to a statement. So a statement is generated. So that generated statement goes into pseudocode and data structures, which is our program. It determines the actions that are going to be performed with the values that are given, and has the data structures available to manipulate. Now with that, we build output generators. Okay, we take this and we can run that directly in an emulator. So we can just use those pseudocodes and those data structures and write a program to execute those statements directly. This is what HTML does, and JavaScript, and PHP, and a lot of the so-called scripting languages. To me, it doesn't really make any difference whether it's scripted or if it goes directly to assembler. Assembler then goes into another program that says generate executables. Or we could just go directly to an executable. Or we could go to another language. So if we took JavaScript and we wanted to go to another language, we could do that. It doesn't really make any difference. It's just simply, is it possible to do? Yes. Then if it's possible, we can go to Fortran or Cobalt or PHP or R or G or hundreds of thousands of different languages. And so in reality, when we look at this, there's really only two really differences in any of our compilers, which are the yellow areas, which are determining the syntax and the labeling that we want to put in for each of our tokens. And then we take those tokens and determine the order and what we're going to do in our statement logic. So those are the only two differences. And then Wikipedia has like 710 named common languages, and all of them are identical, except very little differences in any of the two yellow areas. So in effect, I did 29 languages, and I would say in general, not counting the functions, I won't get into the logical part of that, of how that performed, but between any of the two languages, any language out there, it takes maybe 2 or 3 days, maybe a couple of weeks to write or change the yellow areas, because most of them are identical. An assignment statement is an assignment statement, and a conditional. They all have the same, they all perform the same logic with no exceptions. So this is a compiler. But what we're really looking at is really the differences in the compilers. And so our real job here is saying, okay, in my particular case, I don't want the for statement, I want to do a do statement. And so we just change that. Maybe we don't have a while, or we have a do while. Anyway, all these languages, there's very, very little differences. And this is just in the application of a compiler. But if we look at all the other applications, it's pretty much the same. So if we're looking at a line editor or a graphics generator or a visualization tool, they're all doing the same thing. So we break out exactly what we want, what we want to qualify, and so we let the user qualify which statements they want to perform, and then that gets built. And so we can build new compilers in 5 or 10 minutes. Add a new, I want to go to statement. In JavaScript, fine, put it in there. It took me all of 15 minutes to do that. And then I could, jump to labels or whatever I want to do. Or add SQL statements to my language. See, SQL is great for selecting resultant data sets out of a data structure. And so, which is exactly what it does. So we can eliminate databases and do all of our logic within the compiler. And so, in all of our other applications, we're going to be able to do the same thing. Anyway, that's a start of what we're looking at. A very little bit of work to do a compiler if we break these things out, so that now we can have, I have like 29 languages, and I just say, oh, my source code, this is Fortran. Oops, now we jumped over to Cobalt. Now we jumped over to R. Now we jumped over to PHP. It doesn't make any difference. It still goes, the only difference is change the yellow boxes for each language. And then most of the yellow boxes are identical, pretty much. So if you look at C and C++ and C# and Java and JavaScript, they're all pretty much identical. You get into PHP and those are identical. I mean, there's really, the only difference is a dot instead of a plus sign, or a difference in the way they declare comments. I would say comments are probably the most irritating of the changes, but everything else is pretty much the same. Anyway, that's the compiler. Hopefully it makes a little bit more sense of exactly how much work is done to build applications. It's really not that big if we have a system and a technology that can accept this. All right, before I go, I'd like to show you a little bit of the internals of the compiler very quickly. The yellow areas that really define the uniqueness of each compiler. Here I have 29 scripting languages. Some compilers, some are just scripting languages like CSV or HTML, and so, or JSON or whatever language. And each of those have a control file, and in the control file it basically says that if I find this particular sequence, then we call get object start or whatever it is. Here, if I get a 0x is the next characters in my parsing out of the source code, then I call the function get a hex. And get hex, we look at functions. These are all generic functions that any language can call, and if they're specific to a language, like some Python, ways they treat things are different than in another language, then I just simply generate a separate function for them. But in general, most languages use the same format. So this goes through and it gets the next hex values, and then if there's no hex values, then it returns false. Otherwise, it builds a token and returns true. I built so far 89 languages. If we want to extend the language or have a new syntax, we just simply build this. We add it to our control file. So that's how the control files are built and the functions are called to do the parsing. Okay, so that's very easy. And most of these languages, like PHP, call the same functions: get hex, get binary, get octal. Python does get hex, get binary, octal. Same functions, same syntax. And so you see that most of the languages are pretty much identical. The keywords will change based upon the language, of course. MATLAB calls some of the same functions. Here they have check for keywords for MATLAB, which is unique, and so they call that. And PHP, they use different comments, they use the same comments and pretty much in different keywords. So this basically controls, so with 50 or 60 lines of code, actually most of this is just same definition. This just controls the parser. Anyway, and this will probably be simplified over time. I just did it for 29 languages. Once I get 100 or 200 languages in, I'm sure this will be greatly simplified. So here we have PHP, and it starts enter and then exit PHP kind of thing. So we look at JavaScript, and we have some examples. So this is a simple function. For each of these I have different examples of the language. So if I run MATLAB, and it goes and parses out its language, and under JavaScript it'll parse out its language. So we can test this. The whole process here is to make sure that every little bit and byte is testable. That's the input of the compiler, and when I run this for JavaScript, I get on line 5, I get function, bouncing ball, open paren, canvas, close paren. So if we look at our language, line 5 has function, bouncing ball, open paren, canvas, close paren. Get line 44, let's see, 44, here. So we have ball.context.fillStyle equals yellow. So line 44 is ball.context.fillStyle equals yellow. So you see that it's parsing out the statement. We can now send these tokens to the syntax analyzer, which is the right-hand yellow box. So we look at that. So under JavaScript, actually, I made 750 changes to the JavaScript compiler. I'll put an exit statement in and says, okay, you can exit. Just say exit and it'll exit, or exit with a. And we look at the if statement. Some of these get complex. But we start with if, open paren, expression, which means a conditional. And I also said, well, I put in one of my extensions. I said then. I can say if, then, do this statement, else another statement. And statement, it can be complex, so if you braces around it, that S1 takes care of that. And then these call reductions. So if start is if start here, this is the name of the function that is a reducer, which is in here. So here's if start here, which it reduces this, and it sends 1, 2, 3, 4. So P1 is the if, P2 is the open paren, P3 is the expression, and P4 is the close paren. It always does that. And so it creates this if statement and creates a statement and puts in for A the condition, and then the jump is going to be the next statement. Anyway, and then it goes through and calls these other functions. Some of these are complex, but this is one, 80 or 90 lines is the full logic of the conditional, of that conditional. Some of these, like the go to, are 30 or 40 lines. Function is, of course, I have some very extensive extensions on functions because there's all kinds. I can extend the functions and do all kinds of things with functions, but these are the reducers. And so the language looks like this. And so what this does, this builds the compiler. This is the yellow areas. And the reason we're doing this is so that we can dynamically extend the language, the calling of the function based upon a particular character string. All those other boxes within the compiler are fixed. They do not change. The only thing that changes are these tables. And that's what we want to do with with every other application. So if we're creating an operating system, it's the same way. Here we know we need file access or terminal access, or we don't need terminal access, or we don't need keyboard access. Okay, next, what I want to look at is actually creating applications. The standard compilers generate software. Software are simply hardware instructions, but that's very, very difficult to write and read. We can't really understand software. It's all in hardware instructions, so you could write an assembler or some of these so-called high-level languages, but they're unreadable, can't understand them, and are unchangeable. So instead of doing that, what I want to do is go to a natural language so that the basic structures of the application are simply logic units. And then we control those logic units by qualifying them. So here, I just wrote a simple example. So here, create a JavaScript compiler. So it knows basically through those yellow areas what a JavaScript compiler is, and then we include statements, all the statements from JavaScript saying I don't need that statement, but if I wanted to include like C++ declarations, I could do that, and it would work just as well. So you could hard type your data types if you wanted to. Anyway, create your own language. And here we output the x86 executable. So if I wanted to execute as a browser or emulate it within the browser or write my own emulation and debuggers or whatever, I could do that. And then I can save it as a named, universally known name so that I can just reference that as an alias and make it permanent. If I don't put save as, then it will, as long as this script runs, then it will create a new compiler every time. But in general, you would create that once, and then your JS x86 is available for all your other applications. And then we create some sort of syntax that says, okay, the first parameter is the source code. Either if it's a string, it just creates it, or if it's a name, then anyway. And then we can run the application. What we're looking at is programming from this level. You can still include all the functions and things that are unique to your universal world, but from Jane's concept is why force you to write a compiler from scratch? And so that's what Jane is a development systems, and we'll be adding line editors and graphic systems and browsers and operating systems and accounting systems and school management systems and all those kinds of things, and then we just simply create the world that you want to create, and you create your own languages. So that's the end of how we control our software development system. And these we can build visualization tools. Oh, you want to create a compiler, then you could pop up a form and have all the things clickable and do that things, or you can and then that would create this text file, which then gets compiled into the logic units, which get run and saved and so on and so on. So what we'll do is we'll eliminate databases and client-server technologies and all the file directory structures. We don't need any of those, so that basically we're looking at exactly what we want to accomplish. Go to the store and give me a loaf of bread. It's something I want done. Create me, I have a 10-bed hospital system in Houston. Create me something to manage that. That's what we want to say. We shouldn't have to say anything else. So we should be able to create our applications in a few minutes and let the basic structures be done by professional software developers. Not this, every application I build is brand new, which is ridiculous. So thank you. Until next time.